This is a video about terminal potential difference. Here's a circuit. The top of the circuit represents a battery. So the battery has an EMF, but it also has some internal resistance. What does that mean? Well, it means the battery uses some of the EMF when it pumps charges from one terminal to the other. So as a result, the battery heats up and it uses some of the energy. Where does the rest of the energy go that the charges receive? It's given to the external circuit, and so there's some potential difference across this resistor. Let's connect a voltmeter here. So what is my voltmeter connected across? Well, remember, everything on top is the battery. So the EMF is in the battery, but the internal resistance is also inside the battery. So this is just connected across the battery. We are going to adjust this variable resistor. We're going to make the resistance small, and we'll make the resistance big. And as we change that resistance of the external circuit, we'll measure the potential difference on this voltmeter, but we'll also measure the current. So we better add an ammeter. Let me cut the wire right over here and add my ammeter. What does the graph look like? Here it is. I want to try to understand this a little better. Let's pretend that our battery has 9 volts of EMF. It's positive because it's adding energy to the charges. The internal resistance uses up some of that 9 volts, and let's say it takes away 3 volts. What happens to the remaining 9 volts? It is dissipated or used up across this resistor. So there are 2 places where the energy is being consumed. The charges lose some of their potential energy in the internal resistance. They lose the rest of that electric potential energy across the resistor. But what is the voltmeter measuring? It's measuring what we call the terminal potential difference, because one of the battery terminals is here and the other battery terminal is actually over here. What is the terminal potential difference? If we add these up, we get positive 6, which is, wait a second, that's how much this external circuit uses. So the terminal potential difference is simply the potential difference delivered to the external circuit, which the external circuit then consumes. So let's try to understand this graph. I'm going to make up a number and give the internal resistance 2 ohms. And we'll start off by giving the external resistance the exact same amount, 2 ohms. Here's where we are on the graph, right in the middle. And when we think about that, each of these is using half the EMF because they both contribute half of the total resistance. The current is right in the middle. The total resistance is 4 ohms, which is a moderate amount. So we're moderately blocking current from flowing out. What if I turn this all the way down to 0? That's kind of drastic, and here's where we are on the graph. We're all the way over at the edge. The current is really high all the way over here because there's very little resistance in this circuit, and so it's easy for charges to flow out of the terminal. Why is the terminal potential difference all the way at the bottom? Because if this resistor has 0 ohms, it contributes nothing to the total resistance, and hence it consumes none of the EMF. So the voltmeter measures 0. What if I do something less drastic? I turn this up to 4 ohms. Here's where we are on the graph. Try and guess. We're right here. If this is at 4 ohms, then we've got more resistance. And so there's less current. It's harder for charges to flow out. But what about the value of V? Well, remember, the voltmeter is essentially measuring how much voltage is delivered to the external circuit. And if this is a higher resistance, it's going to use up more of the EMF. So now more of the EMF, more potential difference, is being delivered to the external circuit, and the voltmeter gets a higher reading. Let's do something even more drastic and turn this all the way up to 2,000 ohms. Where are we on our graph? We're all the way at the y-intercept. So there is no current flowing out. The x value is 0. Why? because there is huge resistance in this circuit, so basically no charges are flowing out. What about the value of V? Well, if this is huge, then it basically makes up all of the resistance in our circuit. And so the 9 volts is all being dissipated across this. It's hogging the EMF because it has such a huge resistance. And so all 9 volts is delivered to the external circuit, and the terminal potential difference would be 9 volts. So what's the pattern? A big external resistance implies a large potential difference. If this is 2000 ohms, it's going to hog all 9 volts. But a big external resistance also implies small current. And we can understand that from the equation. When R is huge, dividing gives us a very low value of I. But there's another way to see this graph. The EMF is divided across the external circuit and the internal resistance. But we can take the internal resistance and write it as I times the internal resistance, little r. We realize that V term, that's what we're measuring on the y-axis. Our voltmeter is measuring on the y-axis how much of the EMF is delivered to the external circuit. And what's our x value? It's current. We can rearrange this to show y equals minus the resistance, internal resistance, times x plus the EMF. And when we compare that to y equals mx plus b, what's m? What's the slope? It's negative r. So the slope of this graph is negative the internal resistance. And the y-intercept is this term right here. It's the EMF.